Thanks for joining me in today's lesson. In this first tutorial, we will solve exponential and logarithmic equations. We are in section 7.6 in our textbook, and we're talking about exponential and logarithmic equations. We will first look at exponential equations. Exponential equations have the variable in the exponent. In order to solve these, our first step and most important step is to isolate the base. We have to identify what the base is, and bases are just raised to exponents, and the base must be isolated before we can begin. Once the base is isolated, step 2 says we will convert from exponential form to logarithmic form. And we'll remind ourselves how to do that. And then once we've done that, it should be pretty simple. We will use the change of base formula and our calculator to evaluate our solution. And let's round to 3 decimal places today. So let's look at our first example. Example 1, we have 7 raised to the 9x power equals to 15. This is an exponential equation because the variable that we're looking for is in the exponent. Our base is 7 because that's the number that's being raised to an exponent, and since it's already by itself, we've already isolated it. So our next step is to convert. Remember, we took exponential equations and converted them into logarithmic equations. We write the log of the log symbol. The base, which is 7, is the subscript of the logarithmic symbol of the 15, and this will always be equal to the exponent, which in this case is 9x. Logarithms represent exponents, so logarithms will always equal the exponent. So this is converting from exponential form to logarithmic form. The log base 7 of 15 is just representing some number. The calculator will be able to figure that out for us. And then this 9 times our x, well, the 9 has to go away, so I'll just divide by 9. And then I will have x all by itself, and I will have solved it. So x is going to be equal to this. It's going to be approximately this number that I'm about to get from our calculator. So I want you to practice using your approximating symbol. It's not an equal symbol, it's an approximate symbol. So let's pull up our calculator. I'll slide it on over here. Now I've got the newer operating system, so when I push math and I go up, I've got the log base program, I guess. I'm going to press enter on that. So it's going to give me an area for the base, which I'll put in as 7. And then I'll use the arrow button to get over here to the 15. So there's the log base 7 of 15, and then I just have to divide by 9, and I will have my answer, 0.1546. Since I'm rounding to 3 decimal places, I'm looking at my third number, which is a 4, but because the next number is 5 or higher, I'm going to round this 4 up to a 5. So 0.155 will be my final answer, 0.155. Now, just in case you did not have the newer operating system on your calculator, you will need to use the change of base formula. The change of base formula says that if you take the log base 7 of 15, then you can push the common log button, the common log of 15, and then divide that by the common log of 7. So again, log base 7 of 15, you'll take the log of 15 and divide by the log of 7. And then I'll take that number and divide by 9. And I'll do that individually. I'll still get the same exact answer as if I had plugged it in the first time. Great. Let's look at example 2. Example 2, we have our base of an e. And that is our base. I know that the base is e because that's the only thing that's being raised to our exponent. Clearly, this base is not isolated. We have this 16 to deal with, so I'll subtract 16 from both sides. And I'll have negative 3 e to the 2x is equal to 5 minus 16, which is negative 11. The base is still not isolated because we have this negative 3 as a coefficient. That's just being multiplied to my power here. So I'm going to divide by negative 3, and then I will have e to the 2x is equal to a negative divided by negative is a positive, so I'll just leave that as an improper 11/3 fraction. Now that my base is isolated, we must isolate. Now that we are isolated, we can convert out of exponential form and into logarithmic form. So let's do our conversion. This time, since I know that I'm dealing with base e, I'm going to use my special natural log symbol, and it's going to be the natural log of the 11/3 is equal to my exponent of 2x. Remember, when you have log base e of something, I guess of 11/3, that's equal to the natural log of 11/3. So I'm just using my natural log symbol. Again, this is just some number that the calculator will deal with, and then I will divide by 2 to solve for x. And I'm going to have x is approximately, now I need to plug this into my calculator, and let's see what we get. So I have the natural log of 11/3. I'll close the parenthesis around that, and then I will divide it by 2. And I get 0.6496. Again, I'm rounding to 3 decimal places, so this 9 has to go up because the 6 is to the right of it. But 9 can't go any higher, so 49 has to go higher. 49 will go to 50. So 0.650 will be the correct rounding to 3 decimal places. 0.650. And there's our final answer. So that's how we will solve exponential equations. We will isolate our base, then we will convert into logarithmic form, and then we will plug into our calculator and round to 3 decimal places. Let's look at some logarithmic equations. We can use our properties of logarithms, we've already dealt with those in previous tutorials, to condense each side to a single logarithm. It's important that we're dealing with a single logarithm. Then we can convert into exponential form using or we can use our property of equality. And let's talk about that. If we have the log base a of x is equal to the log base a of y, as long as you're dealing with logarithms that have the same bases, you must understand that these two numbers have to be identical. And that's a pretty simple property to deal with. This is the property of equality with logarithms. And that's in example 3. We have the log base 5 of this quantity 4x minus 7, and that's equal to the log base 5 of this quantity x plus 5. Well, as long as the bases are exactly the same, we know that these two quantities, this 4x minus 7 and this x plus 5, must be identical. And then we have a pretty simple equation that we can solve. We'll subtract x and combine our x's onto one side, so we'll have 3x. Maybe at the same time we'll add 7 to both sides, so we'll have 3x equals to 12. And then of course we'll divide by 3 and we'll be finished. We'll have x is equal to 4. Pretty simple property, this property of equality. Now we can only use this property if we have a single log equal to another single log. If we don't have that, like we have in example 4, we have 2 logarithms on one side and 1 on the other. We cannot use our property of logarithms, a property of equality until we have a single logarithm equal to a single logarithm. So we need to condense these 2 logarithms together. Now remember, there's a property that says that if we have 2 logarithms and we're adding them together, we can condense into one by taking those two things, this 5x, and multiplying it to this 6. This is the product property. If we have the logarithm of a product, we can split it up into 2 separate ones and add the logarithms separately. Or if we have 2 logarithms added up, we can condense them into a single thing by multiplying the numbers. And then we have a single logarithm equal to a single logarithm. And then I can use my property of equality. I know that this and this must be the same. I know I'm dealing with the same bases. I don't see them, but I know that they are base e. because I'm dealing with a natural log. 5x times 6, of course, is 30x. And here's my 10x plus 40. Solving for x, looks like I'll probably subtract 10x and bring that over to here. And I will have 20x is now equal to 40. And then one last division, divide by 20, and we have x equals 2. Perfect. So if you have multiple logarithms added or subtracted, please go back to your properties of logarithms and remember how to condense them into a single term, and then you can use your property of equality. Except here in example 5, something's a little bit different. We have a logarithm, but it's not equal to another logarithm. So we cannot use the property of equality for logarithms because we don't have that. We don't have a logarithm on this side. This is a type of logarithmic equation that would simply convert into exponential form. Remember, when we have a logarithm that's equal to a number, this number represents an exponent. That must be an exponent because that's what logarithms are equal to. So what's my base? Well, my base is this little subscript here, and that's 4. My exponent, we all know, is on the other side of the equal sign, which is 3, so we're cubing the 4. And that will be equal to my number, which is this expression 5x minus 1. So the logarithmic form of this equation is not very helpful, so we convert it into exponential form this time. 4 cubed is 64, and then we can easily solve for x. Let's add 1. Get that out of here. 65 is now equal to 5x. And let's divide by 5 and we'll have our final answer. Oops, I wanted to change color. Divide by 5. And if you don't mind, I'll also use my symmetric property and bring my x over here since I like that on the left side. 65 divided by 5 is 13. And there we go. Thanks for watching this tutorial on solving exponential equations and logarithmic equations, and we'll see you in class to practice this some more. Alrighty. Bye-bye.